Hi everyone. In this video, I'm going to go through section 2 of your lab handout, which is recording the output of the differentiator circuit for several different input signals. Now, before we do that, since we're only looking at the differentiator portion and not the entire frequency discriminator circuit, I'm going to disconnect the output of the differentiator from the input of our voltage follower. Now we can set up our channel 1 and channel 2 measurements. So I'm going to connect both the scope channel 1 negative and scope channel 2 negative cables directly to the ground rail. These are labeled 1 minus and 2 minus on your 82. Next, I'm going to connect the scope channel 1 positive cable, which is solid orange and labeled 1 plus, to the input node of our differentiator circuit. And I will connect the scope channel 2 positive cable, which is labeled 2 plus on your 82 and is solid blue, directly to the output of the differentiator. Now we're ready to actually perform the frequency response measurement of our differentiator circuit. So to do that, first double-click on the Waveforms app. Now the very first thing that we need to do is we need to enable the positive and negative power supplies and set them to +5 and -5 volts. So click on the supplies application, change the positive power supply V plus to 5 volts and the negative power supply V minus to -5 volts. And then click the button that right now says master enable is off, and it should now have a green check and then read master enable is on. This means that both the positive and negative power supplies are enabled and set to +or -5 volts. Now we're going to specify the input from the waveform generator. So click on WaveGen. For this part of the lab, we're going to use a single sinusoid at various frequencies and 1 volt peak to peak. The first frequency measurement that you'll be performing is a frequency of 100 Hertz. So change the frequency in the WaveGen to 100 Hertz. And since this sinusoid has a peak-to-peak voltage of 1 volt, the amplitude would be 0.5 volts or 500 millivolts. Once the waveform generator has been configured to produce a sinusoid of various frequencies and 1 volt peak-to-peak, press Run to actually input this sinusoidal voltage waveform to the input of our differentiator circuit. The last step is to actually head over to the oscilloscope window and view our output. So to do that, click on Scope. I'm going to change the time division from 1 millisecond per division to 5 milliseconds per division. I'm going to set up my peak-to-peak voltage measurements, which will allow us to calculate the magnitude of the frequency response function. As you can see, I've added peak-to-peak measurements for both the channel 1 and channel 2 voltage waveforms. And now I'm going to run a single acquisition of our output. So I'm going to press single. And when I do that, we can see that our input voltage waveform is in yellow. It has 1 volt peak-to-peak or 0.5 volt amplitude. And then this blue sinusoid is our output waveform, which is a constant times the derivative of the input voltage waveform. Since we're happy with these results, I'm going to head over to Export. Under the Image tab, press Save to save an image of the oscilloscope plot. Now, in the section 2 of the lab handout, you're asked to perform frequency response measurements for frequencies of 100 Hertz, 500 Hertz, 1 kilohertz, 2 kilohertz, and 5 kilohertz. I'm just going to perform the 100 Hertz and the 5 kilohertz measurements, and I'll let you complete the measurements in between. So for the 5 kilohertz frequency response measurement, I'm going to head back to the waveform generator and change the frequency of the waveform generator from 100 Hertz to 5 kilohertz. I can head back over to the oscilloscope plot. I've adjusted the time division to be 100 microseconds per division, and by pressing single, we get a single acquisition of our output. Alright, so we finished performing the frequency response measurements for our differentiator circuit. Now what we're going to do is we're going to apply a sync input function to the input of our differentiator circuit and then view the output. Now, unfortunately, the sync function isn't built into the waveform generator's pre-programmed signals, so we have to configure it manually. To do so, in the WaveGen tool, instead of choosing a simple WaveGen configuration, choose the custom type, press New, and then head over to the tab that's called Math. In this text box here, enter in the sync function, which is sine of 100 times pi times x over 100 times pi times x. Uncheck this normalize option, and then since we want our sync function to be symmetric, instead of choosing x from 0 to 1, choose x from minus 0.5 to 0.5. Now click Generate to view what the sync function will look like, and since we're happy with it, click OK. Once we have the sync function entered into the waveform generator, we have to change the frequency and the amplitude. Now, I already had these set before the video started, but make sure that the frequency of the sync function is set to 5 Hertz, which is a very low frequency, and the amplitude is set to 3 volts. The reason why we need to use such a low frequency like 5 Hertz is so that we don't keep seeing the sync function repeating over and over again on our oscilloscope plot. Once the sync function has been configured in the waveform generator, press Run, and then we can head over to our oscilloscope plot to view a single acquisition of our output. And when we do so, this is the sort of plot that we get. The yellow curve represents the input waveform, which is a sync function. And then this blue curve represents the output of the differentiator for this specific input waveform. All right, we finished viewing the output of the differentiator circuit when the input is a sync function. Now what we're going to do is we're going to look at the output of the differentiator when our input is a triangle wave. So to do that, head back over to the simple waveform configuration, change the type to triangle. We're going to use a frequency of 100 Hertz for the first measurement and 1 kilohertz for the second measurement, and change the amplitude to 2 volts. All the rest of the fields offset should be 0 volts, symmetry 50%, phase 0 degrees. These can all be left the same. Now that we have our triangle wave configured into the waveform generator, we can view our output on the oscilloscope by heading over to the oscilloscope screen and performing a single acquisition of our output. And when we do that, this is the plot that we get. Now, just for reference, right now I have a time division of 5 milliseconds per division. My channel 1 is on 1 volt per division, and channel 2 is at 100 millivolts per division. Notice how our input waveform is a triangle wave, and the output waveform is a square wave. And that makes sense based off of theory, since our circuit is acting as a differentiator. For the second measurement, we're going to use, instead of 100 Hertz as the frequency of the triangle wave, we're going to use a frequency of 1 kilohertz. I'm going to head back over to my oscilloscope screen, change the time division to 500 microseconds per division, and then press single to perform a single acquisition of the output. Also, I can change my range. Instead of having 100 millivolts per division, I'm going to use 1 volt per division, and this is the sort of output waveform that we get. Now notice how by increasing the frequency of the input waveform from 100 Hertz to 1 kilohertz, that our differentiator circuit is for the most part differentiating, but we see these sort of smooth sections as opposed to a square wave. And in the post lab, you'll analyze why this sort of behavior is happening. In any case, this is the output waveform that's expected. So head over to the Export tab and then save an image of the oscilloscope plot. The last step is to actually perform measurements on the entire frequency discriminator circuit as a whole. So to do that, we connect the output of the differentiator to the input of the voltage follower, and then move the scope channel 2 positive measurement from the output of the differentiator to the output voltage of the envelope detector. We're going to use the waveform generator to apply a 4-volt peak-to-peak sinusoid at a frequency of 1 kilohertz. So keep the frequency at 1 kilohertz and make sure that the amplitude is set to 2 volts or 4 volts peak-to-peak. Now that we have a sinusoid configured into the waveform generator, I'm going to head over to the oscilloscope and perform a single acquisition of the output. As you can see, the output of our frequency discriminator circuit is pretty much purely DC output that is reflective of the frequency of our input sinusoid. Now, in order to test that our frequency discriminator circuit is working, we need to test our frequency discriminator circuit for 2 sinusoids at different frequencies and see that the output of the frequency discriminator circuit increases when we increase the frequency of the sinusoid. So I'm going to change the frequency of the sinusoid from 1 kilohertz to 2 kilohertz, but I'm going to leave the amplitude the same. And if I head back over to the oscilloscope plot and perform a single acquisition, we see that the output of the frequency discriminator circuit has increased, which makes sense because we increased the frequency of our sinusoid, and the circuit as a whole should be acting as a frequency discriminator whose output is proportional to the frequency of the input. Make sure that for both the 1 kilohertz and 2 kilohertz measurements of the frequency discriminator circuit that you save images of your output by heading over to export and then saving an image of the oscilloscope plot. All right, so we finished characterizing the major components of the frequency discriminator circuit in section 2 of your lab handout, and in the next video, we're going to use the frequency discriminator circuit to decode a message that has been encoded using binary FSK.